Hello everyone. Today we look at how Alcatel-Lucent Enterprise enables long-distance connectivity using our validated optical transceivers, optical amplification, and WDM solutions. Whether you need simple point-to-point links or high-capacity multi-wavelength transport, Alcatel-Lucent Enterprise provides flexible DCI options tailored to distance, bandwidth, and resiliency requirements. So let's see how we can leverage dark fiber to connect remote locations. For example, branch offices, data centers, remote sites with dedicated private optical links. First, let me clarify what we mean by dark fiber. Dark fiber refers to existing optical fiber infrastructure that is currently unused, essentially a fiber asset with no active electronics on it yet. It is a resource that's already there, but simply not carrying data. Why is this interesting to us and to our customers? Because by lightening the dark fiber ourselves, adding our own transceivers or optical gear, we can create a private, dedicated link between any two sites. That gives many advantages compared with relying on public internet or leased circuits. Specifically, dark fiber links offer cost-effective bandwidth, since we are not paying recurring lease line fees and fiber itself often has plenty of spare capacity. Full control. We manage exactly how the link behaves, bandwidth, latency, security, and we avoid shared network unpredictability or third-party constraints. Scalability. Because once fiber is in place, we can upgrade capacity, higher speed optics, or wavelength multiplexing as requirements grow without laying new cables. Importantly, for many use cases involving only two or maybe three sites, this model does not require deployment of a full SD-WAN solution, which is also in our portfolio. SD-WAN is typically designed for large-scale networks, often with tens or even hundreds of distributed sites. In scenarios with only a few sites, implementing SD-WAN can introduce unnecessary complexity and cost. Instead, a point-to-point dark fiber or dark fiber plus optical gear can provide simpler, high-performance, and affordable connectivity. Light travels extremely fast, about 300,000 kilometers per second in vacuum. But inside glass fiber, things slow down because of the glass refractive index. In practice, that means around 180 to 200,000 kilometers per second, which equates to roughly 5 to 5.5 microseconds per kilometer. So for a 100 kilometer span, pure propagation delay is about 0.5 milliseconds one way. That sets a theoretical minimum latency floor. No matter how good our switches or WDM equipment are, we can't beat physics. A fiber is made of a core and a cladding. The core has slightly higher refractive index, so light stays trapped inside by total internal reflection. In single-mode fiber, because the core is tiny, only a single propagation mode exists, meaning virtually no mode-induced dispersion. That's why single-mode fiber is perfect for long-distance, high bandwidth, and WDM. In multi-mode fiber, core is much larger. Multiple modes can propagate, but they follow slightly different paths, some zigzag, some more straight, causing modal dispersion. Pulses arrive at slightly different times, which limits bandwidth and distance. As light travels, some of its energy is lost. Main fundamental causes are scattering. Microscopic irregularities in glass cause light to scatter out of the core, and absorption. Impurities in glass absorb photons. On top, every connector, splice, band, patch cord adds extra loss. That's why a real-world fiber route might have significantly more loss than just fiber length multiplied by attenuation. Typical number for high-quality single-mode fiber at 1550 nanometers are 0.25 to zero point 0.4 decibel per kilometer, while for multimode fiber, attenuation is much higher, around 3 decibel per kilometer at 850 nanometers and around 1 decibel per kilometer at 1300 nanometers. To know whether a fiber link will work, we must compute total losses and compare with transmitter-receiver optics power budget. That is, fiber loss plus connector and splices loss plus margin must be less than transmitter output reduced by receiver sensitivity. Total link can be calculated but also measured. Total link loss budget is a theoretical estimate of how much optical power will be lost over the entire fiber link before actually laying or testing the fiber. It comprises all passive loss contributors and extra losses for bands, margins, and safety allowances. Fiber attenuation per kilometer multiplied by fiber length accounts for the inherent loss of light as it travels through glass. For example, typical single-mode fiber shows 0.25 to 0.35 decibel per kilometer depending on wavelength. Connector and splice losses come from physical imperfections. Each connector pair may add 0.3 to 0.75 decibels, and each splice typically adds 0.1 to 0.3 decibels, depending on splice quality and fiber type. Band loss margins and safety margins are added because real-world fiber may be bent, re-terminated, or degraded over time. We always include a margin to account for future degradation, maintenance, or unexpected losses. Common practice is to leave several decibels as headroom. After installation, we measure the actual loss using the optical loss test set, calibrated light source on one end and a power meter on the other. This provides a precise insertion loss value. The measured insertion loss, in this sample 15.8 decibels, is compared against the application's maximum allowed loss or power budget. If the measured loss is within the allowed limit and leaves a margin for future degradation, the link passes. The power budget defines the maximum optical loss in decibels that a link can tolerate and still work. We calculate power budget based on worst-case specs, using the minimum output power of the transmitter and the receiver's sensitivity threshold. That ensures that even under the worst-case device conditions, after aging, temperature changes, and so on, the link remains viable. Link loss is the total loss the signal will suffer over the fiber link before reaching the receiver. This includes attenuation along the fiber, losses at connectors, losses at splices, plus any other losses that can happen due to bending, repairs, and future reterminations. We add all these losses in decibels, which is why loss budgeting is additive. Even if your initial calculation suggests link loss slightly under power budget, for instance 18 decibels loss versus 20 decibels budget, you should not treat that as safe. Real-world conditions degrade over time. Connectors get dirty, splices might age, fiber might be re-terminated, external bends or stress may add loss. By building in a power margin, ideally 2 to 5 decibels or more, you leave headroom for those uncertainties. Always use conservative worst-case values for attenuation and splice connector losses, never best case or ideal values. That helps avoid underestimating loss, which could lead to link failures or marginal stability. Fiber specifications themselves, length-based loss per kilometer, plus counts of connectors and splices must be carefully considered. Before you propose a solution, which transceivers, whether to use the WDM, whether amplifiers are needed, whether existing fiber is acceptable, always run this calculation. If power margin is comfortably above zero plus margin, you can proceed. If not, you'll need a higher power module, cleaner fiber, fewer splices connectors, or add regeneration amplification. After installation, always verify with actual measurement OLTS. The calculation is design phase estimate. Once the link is deployed, perform an insertion loss test to measure actual loss and compare against your budget to confirm that real-world installation meets design assumptions. Any significant degradation or loss beyond margin must be addressed before going live. On this slide, we are showing a real example of how Alcatel-Lucent Enterprise validates long-reach optical transceivers and how to interpret the key parameters that drive their rated reach. With every release of OmniSwitch AOS, we perform official transceiver validation for each product line. This includes long-reach optics such as 40 km and 70 km SFP modules. The supported list of transceivers is documented in the OmniSwitch AOS Release Transceiver Guide, which you can use as a reference when designing or proposing solutions. This validation ensures that the module works reliably in the Alcatel-Lucent enterprise switching environment. Use the validated transceiver guide as your trusted reference. This avoids proposing optics that are not validated on Alcatel-Lucent enterprise gear or that technically should work but aren't supported. In this very example, on the left we have SFP gig LH40, gigabit SFP for 40 km distance. On the right, we have SFP gig LH70 transceiver for 70 km distance. Both modules share similar nominal optical characteristics. Optical power output is between 0 and 5 dBms, while receiver sensitivity is minus 22 dBms. This equates to a raw power budget of 22 dBs. In basic link budget terms, the 22 decibels budget would be sufficient for links with 19 decibel of loss if you also leave a typical engineering margin of 3 decibels. Despite having essentially the same power budget on paper, the two SFPs are rated for very different distances, 40 km versus 70 km. The reason comes down to attenuation in the fiber, which is a function of wavelength. 1310 nanometers used by the LH40 has higher attenuation, typically 0.32 to 0.36 dBs per kilometer in a single mode fiber. 1550 nanometers used by the LH70 has significantly lower attenuation, typically 0.19 to 0.25 dBs per kilometer. When you multiply those per kilometer attenuation values by distance, the 1550 nanometer module can reach nearly twice as far for the same optical budget. Also shown on the 40 kilometer module is maximum input power. This is important because if the optical signal is too strong at the receiver, you can saturate or damage the photodiode on the receiving side. In a link with amplifiers, passive devices, or unusually short span with strong signals, you must watch this number to avoid receiver overload. On this slide, we are going to cover how optical amplifiers extend reach beyond what simple long-reach transceivers can achieve. This is crucial when we design links that span distances where even long-reach SFPs, like 40 km or 70 km modules, either can't cover the span or we want more margin and flexibility. Optical amplifiers compensate for fiber attenuation. They boost the optical signal within the fiber without converting it back to electrical form. This means you can overcome the limits of transceiver power budget alone. In other words, instead of relying only on transceivers' built-in transmitter power and receiver sensitivity, amplifiers raise the signal power along the path so that it stays above the receiver's sensitivity threshold. A booster lives right after the transmitter. Its job is to increase the optical power injected into the fiber, balancing initial losses of connectors and filters and maximizing the launch power. It can boost multiple wavelengths at once, which is ideal when you are operating a WDM systems. Booster amps improve reach by raising the baseline power level that enters the fiber. Inline amplifiers are placed mid-span, wherever cumulative attenuation threatens to drop the signal below acceptable levels. They are typically deployed every 80 to 100 km of fiber, depending on fiber loss and channel count. In practice, we use them as a last resort if just boosting at the ends doesn't get you the power margin you need. Unlike regeneration, inline amplifiers don't convert to electrical. They are fully optical, so latency stays low and link simplicity is preserved. preamp is placed just before the receiver. Its purpose is to enhance weak incoming signals. This improves reliability and increases the effective sensitivity margin of the receiver. Preamps can help avoid bit errors or link drops on very long or high-loss fiber spans. Simple to deploy and effective at making lower power optical signals detectable at the receiver. Any of these amplifiers, booster, inline preamp, can be used independently, but they are usually deployed in combination for very long links. Together, this arrangement allows spans of hundreds of kilometers, far beyond what is feasible with just long-reach transceivers. Let's walk through the simplified example shown on the bottom right of the slide. Assume 200 km of fiber at 0.2 dB per kilometer, which results in 40 dB total attenuation. The booster puts out plus 25 dBm of optical power as the signal enters the fiber. After 200 km, that signal is attenuated by 40 dB, roughly minus 15 dBm, arriving at the far end. A preamp with a sensitivity range of minus 35 to 0 dBm easily accommodates that level, so the signal is reliably boosted into the receiver. That gives a power margin that ensures stable link performance even with these large spans. With this slide, I would like to introduce the concept of wavelength-division multiplexing, or WDM, and how it increases bandwidth over existing fiber infrastructure. As pre-sales engineers, we often get asked about how to scale capacity without laying new fiber. WDM is one of the most effective architectural approaches to do exactly that. WDM increases the utilization of a single fiber by assigning each service or channel to its own optical frequency, or wavelength. Since different wavelengths do not significantly interfere with each other physically, they can be combined or multiplexed onto the same fiber and carried transparently from one end to the other. Instead of one service per fiber, with WDM you get many independent services on one fiber pair, each service riding on its own wavelength. On the table below, we compare dense WDM and coarse WDM, the two main flavors used in optical networking. With dense WDM, you can have around 160 channels, a large number of distinct wavelengths. This enables extremely high aggregate bandwidth. It supports point-to-point, rings and mesh topologies due to dense wavelength planning and ROADMs. Designed for very long distances, hundreds to thousands of kilometers, often using optical amplification along the fiber. Used for modern, high-capacity carriers and data centers interconnects, capable of carrying 10 gig, 100 gig, even 400 gig and beyond on each wavelength. It is more expensive because of tighter spacing, more precise lasers, and advanced optical components like ROADMs and amplifiers. Coarse WDM can have 8 or 16 channels, fewer distinct wavelengths than DWDM. Typically is used in simple point-to-point topologies, not full ring or mesh. Reach of CWDM is typically less than 80 km due to larger channel spacing and no inline amplification built in. It is usually limited to 10 gig wavelengths, although technology is evolving. It is less expensive in equipment and optics compared to DWDM. On this slide, you can see how optical networking elements combine into nodes and how different architectures are used depending on scope, reach, and complexity. On the left side, we have a simplified view of an optical node, the building block of optical networks. There is optical transporter that converts client electrical signals, Ethernet, fiber channel, and so on, into a specific optical wavelength or band. It modulates the signal onto the optical carrier. Optical multiplexer or demultiplexer element combines multiple wavelengths onto a single fiber and splits them apart on the receiver side. This is the heart of wavelength-division multiplexing. Wavelength router, often implemented with ROADM or wavelength selective switch, routes different wavelength channels to and from different directions or ports. It allows flexible wavelength management without optical to electrical regeneration. The amp block at the top and the bottom represents optical amplification that compensates attenuation over long spans. This combination forms a network node that can insert, drop, route, and pass wavelengths, essentially the optical equivalent of a router or switch, but at the wavelength layer. On the right side, we can see a few typical network topologies used in optical systems. A linear topology is a point-to-point connection between two sites. It is simple, cost-effective for single-link applications, connecting two data centers or campus sites over dark fiber with WDM. With the hub topology, you connect a central hub node to multiple sites, useful for star-like architectures where many edge sites terminate into a central aggregation node. This is common for enterprise backbones or regional aggregation rings. With ring topology, you have multiple nodes connected to each other in a closed loop. Ring topology provides path diversity and redundancy. If a fiber cut occurs on one segment, traffic can be rerouted in the opposite direction of the ring. It is used extensively in metro regional networks for reliability. Of course, there can be a mixed or hybrid topologies, and real networks often combine above-mentioned topologies. Star and linear at the access layer, ring at the regional layer, and mesh at the backbone layer. Here are a few questions that can be asked to help define the right decision solution. Do you expect simple site-to-site connectivity or multi-site aggregated traffic? How critical is continuity in the event of fiber cuts? Is your environment metro, regional, or wide area? And, for instance, do you expect growth in capacity, more wavelengths, or future DWDM expansions? This concluding slide shows how Nokia's data center interconnect portfolio covers a wide range of enterprise and telco requirements, from simple, cost-effective solutions to high-capacity, scalable transport platforms. Nokia's DCI portfolio isn't one-size-fits-all, it's composable. Customers can start small and scale without hardware refresh or forklift upgrades. Whether the buyer is an operator or an enterprise IT architect, there is a validated, standardized option that matches their use case. Management, visibility, and automation tie everything together, making it not just a transport solution but a manageable one. As you position this solution with customers, always return the discussion to requirements first: environment, reach, encryption, redundancy, and client services. With Nokia portfolio, we are targeting telco operators with complex distributed traffic and strengthened SLA requirements, but also enterprise and cloud data center connectivities where simplicity and high throughput matter most. Nokia platforms are designed to span tens of kilometers, hundreds, or even integrate into wide area networks for those extended distances with optional amplification, DWDM, and resilience. Nokia platforms support inline encryption options at various layers, making DCI both secure and compliant for regulated industries. Many of these platforms support redundant control planes, redundant power, ring protection, and resilient optical paths, which becomes a strong differentiator in mission-critical environments. The last but not least, the portfolio supports rich client services at Layer 2 and Layer 3 or fiber channel from 10 gig throughout 800 gig throughput with flexibility in encapsulation and grooming. To summarize, we can say that Nokia's DCI portfolio spans from compact transport system suited to enterprise IT data center interconnects up to modular carrier-grade platforms for telco backbones. It covers a wide range of distances, supports optional encryption, high redundancy, and a broad set of client services, all manageable under a unified suite. The idea is to match customer requirements with the most cost-effective, scalable technology rather than one-size approach. Thank you all for watching this webinar. If you have any further questions, please contact your Alcatel-Lucent enterprise representative.